Here we begin a chapter on exchangeability, where we will discuss infinite dimensional arrays in the presence of some symmetry under permutations. And more precisely, we will describe how this symmetry enforces special structure on the distribution of this array. And we begin with the most classical result of this type, the so-called Finetti theorem for exchangeable sequences. So let me begin with the definition. We say that a sequence of random variables is exchangeable if the distribution of this sequence under some relabeling of the indices is the same as the distribution of the original sequence. And this is for any one-to-one function on the indices. Okay, so in other words, since this is really a statement about finite dimensional distributions, this means that if you take any finite collection of the indices, the order of the indices doesn't matter, and precisely what these indices are doesn't matter. Okay, the most important way in which this definition will be used is the following. So let me state this from the beginning, that if you take any subset of your indices which is infinite, then the distribution of this subarray indexed by L in this set is the same as the distribution of the original array. And again, because the order doesn't matter, you can arrange the indices in this subset in arbitrary order. So for this reason, we will just ignore specifying the order of the indices in the subsets. Now here I implicitly assume that these are just usual real-valued random variables, but of course this definition makes sense if the elements of this sequence take values in basically any measurable set. And in fact, we will often work with such more general sequences. And then the main result that we will prove about exchangeable sequences is the following theorem of Finetti. So it says that if your sequence is exchangeable as above, then there exists a function, a measurable function of two variables on 0, 1, such that the sequence SL is equal in distribution to the following sequence. Okay, where the arguments W and UL for L greater or equal than 1 here are all IID uniform on 0, 1. Now there are different ways one can state Finetti's theorem, and in fact very soon we will restate it in a way that sometimes is more convenient in applications, but here we'll begin by proving this particular statement. And first of all, let me make several remarks. The first remark is that the real line here can be replaced by any so-called Borel space. Okay, so in other words, instead of our sequence being real valued, it can take values in more general spaces, the so-called Borel spaces. And what Borel space means is that there exists a map between this space and a measurable subset of 0, 1. So A is just a Borel set on 0, 1. Okay, such that this map is so-called bimeasurable bijection. So in other words, this function is a bijection, and both the function and its inverse is measurable. And of course, if you can map your space back and forth together with its sigma algebra to a subset, measurable subset of 0, 1, in the above theorem, if you prove the theorem for random variables that take values in 0, 1, automatically you can transfer it to any Borel space just by applying this bijection. So in fact, when we will be proving this theorem, we will just assume that our sequence takes values on 0, 1 instead of the real line. Now, what kind of spaces are Borel spaces? Well, for example, a classical result in real analysis says that all Borel subsets of complete separable metric spaces are Borel spaces. So in particular, once we prove this result on 0, 1, we automatically have it on any complete separable metric space. In my next remark, let me try to explain the role of these uniform random variables that appeared in this statement. So the basic idea here is that these uniform random variables and representation in terms of these variables allows us to encode structural information about measures in a simple visual way. Now, in this section, the results are simple enough that we could prove and state them without using these types of representations. But when we discuss results for two-dimensional arrays in the next section, this really becomes a very useful point of view. And so to get used to this point of view, let me begin with a couple of very simple examples. So in the first example, let's just take one random variable x which takes values in a Borel space. Okay, for example, complete separable metric space. Now, by the result that I referred to above, you can represent a random variable x by some function of a uniform random variable on 0, 1. Okay, so by using that bimeasurable bijection, you can define a function on 0, 1 with values in this Borel space that will have the same distribution as x. And so this means that we can view any random variable in a nice space like this as a function of a uniform randomness. So we can encode them by just a function of a uniform random variable on 0, 1 if we wish. Now let me give another example involving two random variables. So now suppose we have a pair of random variables x and y, where y takes values in a Borel space or a complete separable metric space. In this case, we had an exercise in the first chapter which showed that this pair x and y is equal in distribution to x, and y can be replaced by a function of x and uniform random variable u on 0, 1. So in addition to that exercise, this statement is also proved in the notes under the name of coding lemma. But basically what this statement expresses is the existence of regular conditional probability. So in other words, when a random variable y takes values in a nice space, there exists a conditional probability of y given x. And so this conditional probability, it depends on x, which explains this appearance of x in the function f. But otherwise, this representation simply encodes that you can describe for a fixed x, or you can encode for a fixed x this conditional distribution given x by a function of uniform random variable on 0, 1, just like in the first example above. So when x also takes values in a nice space, let's say a Borel space, then we can combine the two representations above and say that this pair is equal in distribution to some function of some w uniform on 0, 1 and another function of, again, you plug in this h of w for x and u, and here both w and u are uniform on 0, 1 and independent. Okay, and of course you can write this second composition as some new function G of W and U. And so you can encode a pair of random elements in nice spaces by this pair of functions of uniform random variables, right? Where W just encodes the randomness of X and U encodes the conditional randomness of Y given X. And so from this point of view, one can think of the Finetti theorem above as a statement of the following type, that conditionally on something in a nice space, the sequence is IID. Okay, and this something belongs to a nice space, let's say Borel space. Right, and then we can see that this something that we condition on can be viewed as a function of some random variable W, and then conditionally on that, the sequence is IID. So if the W is fixed, the rest is expressed by a function of IID uniform random variables UL. And that's exactly what we wrote above, that SL as a sequence is equal in distribution to some sequence encoded by some function of W and UL. Okay, but hopefully this will become more clear both from the proof and then from a restatement of the Finetti theorem a little bit later in this video. And so now let's discuss the proof of this result. Throughout the proof we will use the following notation. Okay, we will denote by Fi a sigma algebra generated by our sequence SL when indices L belong to this set of indices I for any subset of indices L. And the main step in the proof will be the following lemma, which states that if we have an infinite subset of indices, so the cardinality of this set is infinite, and then we take some index in the complement of this set. Okay, so supposing that such index exists, then for any bounded measurable function f, the conditional expectation of function f of Sj, conditional on the sigma algebra generated by the sequence indexed by the subset I, is equal to the conditional expectation of the same function conditionally on the sigma algebra that includes all indices except index j. And so these two conditional expectations are equal almost surely. And so to prove this, we begin with the observation that we stated at the very beginning, that if you take, let's say, Sj and then this sequence indexed by some infinite subset I in arbitrary order, then this will be equal in distribution to Sj and a sequence indexed by all indices except j. So the exchangeability assumption implied that all such infinite subsequences are equal in distribution. And then we had an exercise in the first chapter which showed that whenever two pairs are equal in distribution, then conditional expectations are also equal in distribution. So more precisely, that expectation of this bounded measurable function of Sj conditionally on the sigma algebra generated by the sequence above, it's equal in distribution to conditional expectation of f of Sj conditionally on the sigma algebra corresponding to all indices except j. Okay, and let's denote this random variable on the left-hand side by x and this random variable on the right-hand side by y. Okay, so here we have equality in distribution of x and y. But then notice that this sigma algebra corresponding to a set I is a subsigma algebra of the sigma algebra corresponding to all indices but j. Right? That's because the set I is a subset of all indices excluding j. And in particular, this of course implies that by smoothing property of conditional expectation, x is just a conditional expectation of y given the sigma algebra Fi. Okay, so we get this additional relationship between x and y in addition to knowing that they are equal in distribution. Okay, now we are going to show that two of these together actually imply that x and y are equal almost surely. Where we will also use the fact that since the function f was assumed to be bounded, x and y are actually bounded, but we'll only need to know that they have the second moment, so they are in L2. And then the fact that x and y are equal in distribution gives us that their second moments are equal. But then if we compute scalar product in L2 between x and y, first we can take a conditional expectation given that sigma algebra above. And since x is measurable with respect to this sigma algebra, we can take it outside, and we are left with conditional expectation of y given the sigma algebra, which we noticed above is actually equal to x. And so we get that this is the same as expectation of x squared. Okay, and now combining these two observations, if you compute the expectation of x minus y squared, when you square it out, you actually get 0, and so that gives us that x is equal to y almost surely. One can also describe this argument geometrically as follows. Namely, if we consider the L2 space on our probability space and this function y, we notice that x was a conditional expectation of y given the sigma algebra Fi, and we know that in L2 the conditional expectation has a meaning of orthogonal projection on the space of function measurable with respect to that sigma algebra. Okay, but on the other hand, we noted above that the L2 norm of x and y were equal, and clearly this means that x and y should be equal. Okay, but in any case, this finishes the proof of this lemma, and using it we will now prove the Finetti's theorem. So here we will take a subset I of our indices, okay, such that both the cardinality of this set and the cardinality of its complement are infinite. And what we will show using the above lemma now is that conditionally on the sigma algebra corresponding to this complement, the random variables in our sequence corresponding to the indices in the set I are independent. Okay, so to show this, let's take any n greater or equal than 1, and let's take arbitrary different indices L1, Ln from this set I. And also let's take n bounded measurable functions f1, fn. And to simplify the notation slightly, I will write fj, meaning fj of s corresponding to this index number j. Okay, so for j from 1 to n. And in order to prove this claim, it is enough to show that conditional expectation of f1, fn conditionally on the sigma algebra f corresponding to the complement of our set I is equal to the product of these conditional expectations. Okay, so this is what we want to show, and clearly this means that random variables corresponding to indices in I are independent conditionally on the sequence indexed by the indices in the complement. Now, in order to prove this, okay, let's take any set in the sigma algebra. Okay, and by definition of the conditional expectations, we want to show that the averages on the indicator of the set of the two sides coincide. Okay, so we start with the left-hand side by taking average of the indicator of this product f1 fn. And in the first step here, what we will do is we will condition on all indices except the last index ln above. And then all these functions and the indicator of A will be measurable with respect to the sigma algebra except the last factor fn. So in other words, we can treat them like constant and simply write this indicator f1 up to fn minus 1 and only apply this conditional expectation to the last factor fn. And now we apply the previous lemma that we proved. Namely, this conditional expectation, we showed that it's equal to the conditional expectation of this fn given any other infinite sigma algebra that doesn't contain the index ln. So we can take here f of n minus I. But by the definition of conditional expectation, this equality here of course means that conditional expectation of the product given this sigma algebra f n minus I is equal to the conditional expectation of the product up to n minus 1 of given the same sigma algebra, okay, times the conditional expectation of the last fn given the same sigma algebra. And of course by induction on n we get the above equation that we want. And in particular this proves the claim above that conditionally on the sigma algebra the random variables with indices in this set I are independent. Okay, and next we are going to strengthen this statement to say that conditionally on the sigma algebra the random variables with indices in I are actually IID. Okay, so they are not only conditionally independent, but they have the same conditional distribution. But of course this again follows from exchangeability, okay, because if we consider any SL and then consider the sequence with indices in this complement, right, the distribution does not depend on the choice of this index L in I. And since the distribution is the same, when we condition on this sequence, let's denote this X, the conditional distribution of SL given X is the same. Okay, which of course now implies that these SLs are IID given X. And just like in our discussion above, this implies that the distribution of X and this sequence SL indexed by this set I is equal in distribution to X. Okay, and here we can encode this conditional distribution given X by some function. Let's say function H, which depends of course on this condition. And the fact that this sequence is IID conditionally on X means that here you can encode them by an IID sequence of uniform random variables on 0, 1. And then finally, let's notice that this X belongs to 0, 1 to natural numbers because we assume that our random variable S takes value on 0, 1, which is a complete separable metric space. So this is a Borel space, and that means we can encode random variable X by a function of uniform. Okay, so just like before, we can say that this is equal in distribution to some function of a uniform random variable W on 0, 1, and you can replace x by this function in this sequence as well. Okay, where now this w and all these ul's are IID uniform on 0, 1. And so finally, if you just take this composition and denote this as a function of w and ul, this gives us a representation for a sequence SL indexed by this subset I. And now by exchangeability, the distribution of any subsequence is equal to the distribution of the original sequence. So that means that the same representation holds for the original sequence. And so this finishes the proof of the Finetti theorem in this particular form, okay, using a representation in terms of uniform random variables. Okay, next we will discuss another point of view on this Finetti theorem in terms of the so-called empirical measure. And let's begin here by considering the case when our sequence is equal not in distribution but given by some function of these uniform random variables w and ul. Okay, and taking values in a nice space, such as Borel space or a complete separable metric space. In fact, because we will deal from now on with probability measures on this space, I will indeed just assume that this is a complete and separable metric space. Okay, which means we have a metric and the sigma algebra on this space is the Borel sigma algebra. Now, if we fix this first random variable w, our sequence becomes IID, and one way to write this is that conditional distribution of this sequence given w is a product measure. So there exists some measure mu that depends on this w such that this is just a product measure. In fact, we know what this measure is, right? This is just a distribution of that function if you view it as a function of u, right? So for a fixed omega. And since u was assumed to be uniform on 0, 1, you can just take Lebesgue measure on 0, 1, and then the image of the Lebesgue measure by this map will be our measure mu. Okay, which again is nothing but a conditional distribution of one element in our sequence given w. Now, the first thing I want to recall here is Varadarayan's theorem for convergence of empirical measures. Okay, which states that when you have an IID sequence on some complete separable metric space coming from some measure mu, so in this case it's this mu w, then this measure is almost surely equal to the limit of empirical measures of your sequence, okay, which is just the average over the first n elements in your sequence of the delta mass at SL. And here we use it conditionally on this w, so we have this almost sure convergence when we view this sequence as an IID sequence. So in other words, the statement here, this almost sure convergence, is first applied conditionally on w. But of course, if we have this conditional statement, it also implies unconditional statement. Right? Because if for every fixed w, the slice of your set has measure 1, that means that the set has measure 1. So this convergence holds almost surely over everything, including w. Now let's also recall that when we talk about convergence of measures here, we really mean weak convergence of probability measures. Okay, so this convergence is on the space of probability measures, which I will denote by P of omega. Right? This is a probability measures on this space with the Borel sigma algebra. And in particular, let's recall that we proved that the space of probability measures can also be viewed as a metric space with respect to the bounded Lipschitz or Levi-Prokhorov metric, and in this case it will also be a complete separable metric space. Of course, this follows from our assumption that omega is complete separable, and this observation will be particularly useful to us in the second part of this section. Now, when we look at the above statement here that for a fixed w our sequence is IID with this measure mu w, okay, let me just copy that statement. So I want to make some additional comments about it. So this distribution of our sequence conditionally on w is a product measure, right, with marginals given by this measure mu w. Now, mu w is itself a function of w, right? As we saw above, mu w can be viewed as an element of the space of probability measures, and from the above definition, it's clear that it's a measurable function of w. And so, in particular, in this conditional probability, if you replace w by w and mu w, you will still have the same conditional probability. Simply because mu w is a measurable function of w, so the sigma algebra generated by both of them is the same as the sigma algebra generated by w. So in some sense, inserting mu w in the condition doesn't add any information. But on the other hand, this conditional distribution on the right-hand side, we see that it's just a function of mu w. And in particular, this means that conditional distribution of our sequence given mu w is also this infinite product of mu w. In other words, given this measure mu w, our sequence is IID from this distribution mu w. And now we can just notice that all these statements are, in some sense, statements about the distribution of the sequence. So we can forget this particular representation using uniform random variables, and we can rewrite all these observations as follows. Okay, so first of all is the existence of the limit above, and this limit is called the empirical measure of the sequence. Okay, so this empirical measure mu, which is the limit of empirical measures of our sequence, it exists almost surely. Now we can view this limit mu as an element in the space of probability measures. So mu is a random element in the space of probability measures. Okay, here it is random because it's just defined as a limit in terms of this random sequence, so it's some kind of random variable. And then finally, conditionally on mu or given mu, our sequence is IID from this distribution. Or in other words, the conditional probability for this sequence given this measure mu is just a product of this measure mu. Okay, so the Finetti's theorem can also be stated in this way instead of using representation in terms of uniform random variables. Okay, in particular, you can define this empirical measure mu, which is in some sense it's just a measurable function of your sequence, and it's an element in the space of probability measures, so it's a random probability measure on your space omega. And then we know that when your sequence is exchangeable, then conditionally on this random measure, the sequence becomes IID with this distribution. And so in fact, in the second part, we will be using the Finetti's theorem in this form. Okay, and finally, let's just show one example perhaps the most classical example of the Finetti's theorem. Namely, when your sequence SL takes two values 0 and 1. Now, in this case, the empirical measure mu is just a measure on 0, 1. Right, so it's encoded just by one parameter, by the probability of the measure of 1. So you have this parameter p between 0 and 1, which is random because this measure is random. And given this parameter p, your sequence is just IID Bernoulli with the probability of success p. So in particular, if you take some outcomes epsilon 1, epsilon n in 0, 1, and if k is their sum, then the probability that your sequence S1, Sn takes these particular values can be computed simply but first by fixing parameter p, and then you just compute the probability for Bernoulli. So success k times, and then failure 1 minus p n minus k times, and then you take average with respect to p. So since this p is random, there exists some distribution of p, let's call it eta, which is a probability measure on 0, 1. And so in other words, because our empirical measure is encoded just by one parameter p, here everything is encoded by the distribution of that parameter. So by one probability measure on 0, 1. And in the second part, we will discuss now two-dimensional versions of the Finetti theorem.